One of the things that I really like about C++ and that I really respect about the C++ design philosophy is that nothing is held back. And we've already noticed the language seems to provide us tons and tons of different ways of doing every task, which is great because we can develop our own idiom. We can decide which features we like as programmers and focus on using those. There is no requirement that you know all of the language because there are so many different avenues you could take. But one other implication of that philosophy is that there are features that we've been using of the language that we are just as able to create ourselves. There's nothing the language provides that we can't create with our own code, which is great. So we've already seen types like vector, which is some sort of smart type, a small appliance, something we can use to represent the abstraction of a sequence. And it shouldn't surprise us to learn we can actually define such things ourselves. And we're actually right now at a sort of turning point in the course. We're about to cross the Rubicon and begin defining our own smart objects. We're going to spend a huge amount of time while crossing the Rubicon wading through the swamps of talking about shapes. Because after years and years of doing this, I've discovered that talking about things like shapes actually does yield some pretty tangible examples to work with. So our goal this week is to talk about how to create these smart objects. We've already seen some of the characteristics of smart objects like vectors and strings. One of them is that they represent some kind of abstraction, which we use from the outside. So we treat a vector like a sequence. We might know by now what a vector is internally, but we don't really need to care to use it. And that's because vectors are encapsulated. We don't know what's going on inside of them because they won't tell us. It's none of our business. And so it's time for us to learn how to create our own small appliances, our own ways of implementing abstractions with their own encapsulation. Before we do that, we have to talk about why we really need this important feature we're going to see this week. So true to the usual way that I do things, even though I think it's useful, and maybe by now you think it's useful, let's just prove it. And we're going to return to this example that we actually saw a few weeks ago. So I'm sure you've seen movies where there's some minor character that shows up in Act 1 who turns out to actually be like the main villain of the film by the time you're at the end of Act 2. This is sort of one of those cases. We actually saw this example in parentheses a couple of weeks ago. So what I have here is a simple structure type I have created to represent a rectangle. There are lots of ways that I could choose to represent a rectangle with types in a language. So here's a rectangle. And I'm going to choose to represent this rectangle just sort of floating in space. So I'm just going to represent it by its width and its height. And we're going to go through various different ways to represent rectangles over the next couple of weeks, because we could choose to represent them in a more complicated way that still allows us to view them through the same abstracted lens. And that's one of the reasons I like using shapes for this, is that they're a very visual representation. It's something that we can actually visualize as we're writing code, even though, yes, it's sort of dry. So I have some basic way of representing a rectangle. And we saw this a couple of weeks ago when we talked about structures. And I pointed out at the time that there are certain things we assume are true of rectangles. For example, that the width is a non-negative value. We might even argue that a rectangle with zero width and height makes no sense. But at the time I pointed out it doesn't make any sense to have a negative width for a rectangle. We also observed that due to the way that structures tend to work, so the structures we've been working with so far in C++ are basically C-style structures. They are buckets of data. Just a bunch of data put together into a container that we can pass around the program. And you might recall that we typically diagram such a thing sort of like this. So I've got a variable of type rectangle, and it contains these two members, and their names are width. Well, maybe I need to practice my handwriting a bit. Their names are width and height. And we pass these buckets of data around the program. The structure type, really, the convenience that it's offering us is the ability to package a bunch of stuff into one convenient package. That's it. And we observe that means that the only real protection that we can put on the members in terms of what values they can contain are the protections already provided by the typing system. So if I want to force width to be non-negative, I guess I could make it an unsigned int. But that really wouldn't help because I want the width to be a real value. So I want it to be 0.5 perhaps. And there is no unsigned double type. So I'm stuck. If I use double, I'm stuck with potentially allowing a width to be negative. And it's worth considering, it's not just about somebody creating a rectangle whose width is negative. It's about other parts of the program that handle rectangles. So down here I have a function that handles a rectangle. What if those parts of the program accidentally perform some invalid modification to our rectangle objects. So that's one issue, is the way we've been treating data so far doesn't give us encapsulation. Because yes, the rectangle has width and height, but the rectangle doesn't get to govern its own existence. If I decide that I don't want negative widths, or maybe I don't want widths that are above 100 or something, I have no way of enforcing that. It's on the honor system. And as I've been pointing out over the last week, one of the key, benefits of encapsulation is the existence, when you have one of those small appliances, of that hard outer casing where you can't see what's going on inside. I go by my toaster and all I know is that bread goes in and toast comes out. I don't know, nor do I have to know exactly what's happening inside the appliance. If I go by a stopwatch, I press the button to start it, I press the button to stop it, I look at the screen or I look at the front at the display to decide how much time has elapsed, but I have no idea what the mechanism underneath is actually doing. That is encapsulation. Not only that I can't see what's going on, but I can't screw around with it. It gets to set its own constraints on how the world interacts with it. That is, I think, one of the defining characteristics of these smart objects we've been seeing in this course so far. And it's something that our current rectangle object does not have. Okay, one secondary thing. This is less of an issue than before, because you could argue this is mostly an aesthetic thing. If we use C-style structures and we write C-style functions, so here I have a function sitting out in the global scope called getRectangleArea. We saw a few weeks ago that I could just call this getArea. The point I want to make today is that really this is sort of coupled to my rectangle type. Obviously I can't get the area of a rectangle unless there is a type for rectangle, so I know that. But really how I compute the area of a particular shape is sort of part of that shape's identity. But the way I've written this is just a function floating around in space. Okay, so you could argue that that's an aesthetic concern, but I think it's a concern nonetheless. Now the third thing is something that it sort of ties into an optimization issue, which, as we should know by now, shouldn't really be much of our concern in a course like this. But it is something to keep on the horizon, which is, suppose that I work with lots of rectangles, and I find myself constantly computing their area. And if you use your imagination and suspend disbelief, imagine that computing the area is more complicated than this. So suppose one multiplication is not the end of the world, but suppose computing the area of a particular shape was complicated. What if I realize that I keep creating rectangles and I never change their width or height, and then I keep asking for their area? What if I decided that maybe what I could do is I could store the area in the rectangle object itself. That way, if I ever need it, I just go grab it. I don't have to bother recomputing it. Now that would work. I could do that. The problem is, if I do that, I take a risk, which is if I store the area, which is dependent on width and height, and I accidentally change the width without updating the area, I end up with invalid data. My data becomes desynchronized. And so issue number 3 here is that the only way to make sure that the area I'm looking at is always correct based on the current width and height is to recompute it every time. But what if I decide that recomputing it takes too long and I want to store it? How do I make sure it's always kept synchronized? If I just have this bucket of data, it would be very easy for one part of my program, one function somewhere, to modify the width but not update the area. And once that happens, I would have no way of catching the error besides, in a paranoid sense, recomputing the area every time that I need it. So these 3 issues, I think, together give us a reason why our current C-style view of the world in terms of these structure types might not be sufficient. And then I'll just show off, before we go to the next example, I will just show off just the basic testing code I'm going to elaborate on in the next few videos. So down here in main, I create a rectangle and I provide its initial values to be width 1, height 1. This is actually a square, interestingly enough. And I guess it's true that a square is a rectangle. We'll just sort of put that in our back pocket for later. And then I make a second rectangle. I initialize it to have width 6 and height 10. And then I print those things out. So I print out the width and height by accessing the members directly, and I call a function to access the area. And what I want to try and prove this week is there is a way to promote rectangle from just being a bucket of data to being something smart, to being something encapsulated that can enforce its own constraints on how it is used. And we'll discover that a type in C++ has the power to decide every aspect of its own existence, how it gets created, when it gets created, who can use it, what they can use, what they can change, when they can change it, and what happens when the object gets destroyed. Every aspect of the object's lifespan can be determined by the type. We can impose constraints inside the type that allow the type to govern every aspect of its existence. And we're going to start talking about this week the basic idea of how do I enforce the constraint that width and height can't be negative? How do I give the rectangle object some agency over what data it contains?